Scaling stateless services is relatively straightforward. If your application gets popular, you simply add more servers behind a load balancer. But databases are different. Databases are stateful systems. They must remember everything: users, orders, payments, or anything else. Every write must be safely recorded, logged to disk, and made consistent. So that coordination makes scaling database much harder than scaling application servers. Eventually, traffic increases. CPU climbs to 95%. Disk I/O saturates. Queries start slowing down. And suddenly, your database becomes the bottleneck. The first solution engineers usually try is vertical scaling, also called scalar. It simply means upgrading the database server with more powerful hardware. You increase RAM, add more CPU cores, and use faster storage. Think of it like upgrading your laptop. If your program runs slowly, you add more memory or buy a faster processor. And for a while, performance improves immediately. That's why many startups run their entire application on a single powerful database server for years. But the vertical scaling has a limit. You eventually hit a hardware ceiling, and the cost increases dramatically. So, no matter how powerful the machine becomes, it is still one machine handling every write request. When a single machine can no longer handle all the traffic, the next step is replication. Think of it like photocopying a popular book in a library. Instead of one database serving every request, we create multiple copies called replicas. The primary database handles all the writes while the replicas handles read queries. This allows the system to scale reads across multiple machines. Large content platforms like news websites or social networks often use application because most users are reading data. But every write still goes through the primary database. So write throughput remains limited. Suppose a user updates their profile picture and refreshes the page immediately, but the old picture still appears. So that's the replication lag. When replication is no longer enough, we need to scale horizontally. This means splitting the database itself across multiple machines. This technique is called sharding. Imagine a huge encyclopedia that has become too large for one shelf. So we split it into several volumes and place them in different sections of the library. Each shard stores only a subset of data. For example, one shard may store the user's information having user ID 1 to 33, another may be for 34 to 66, and so on. So for even distribution of the users, we typically need a sharding formula. Here, it may be kind of like here if we use the key as user ID and we are generating hash of it here and then taking the modulo with the number n so that the distribution of users across multiple shards is even. So this distributes both the reads and writes across multiple machines. The large platforms such as Instagram or Twitter shard their user databases to handle massive traffic. So basically, the sharding is the partitioning of data across independent nodes. Sharding introduces new challenges. Suppose you need to search across all users. In a single database, a SQL join would handle this easily. But with sharding, the data may live on multiple machine instances. So the application must query each shard separately and combine the results. So this turns a simple query into a distributed operation. Another challenge is uneven traffic distribution. Suppose a shard B stores the data for a highly popular account, such as a celebrity. Then that shard will receive more traffic than the other shards, here shard A or shard C. One shard becomes overloaded while the others remains idle. As the platform grows, engineers eventually need to add new shards. But redistributing the data between database servers means migrating millions of rows. So doing that is safely while the system is running is extremely difficult. So sharding takes with it the new set of problems, the cross-shard joins, distributed transactions, global secondary index, rebalancing, and the operational complexity. Earlier we used this formula to decide which shard stores a piece of data. But this formula has a problem. When we add a new database node, the value of n changes, and suddenly almost every key gets remapped to a different shard. That means moving huge amount of data across servers. This process is called rebalancing, and it can involve migrating millions of rows. To reduce this problem, many distributed systems use a technique called consistent hashing. Instead of assigning data directly to a shard using arithmetic, we map both the servers and the data keys onto a circular ring. Each server is placed at a position on the ring using a hash function, and each data key is also mapped to a position on the same ring. To determine where a key is stored, we simply move clockwise on the ring until we encounter the first server. That server becomes responsible for storing that key. This rule is the core of consistent hashing. Now suppose we add a new database server to the system. Instead of redistributing all the data, only the keys that fall between this new server and its neighboring servers, these three, are need to move. All other data stays exactly where it was. This dramatically reduces the amount of data that must be migrated when the system scales. So, consistent hashing allows distributed systems to scale gradually without constantly reshuffling massive amounts of data. So, here is the key takeaway. Scaling a database is fundamentally different from scaling application servers. Application servers are stateless. You can add more servers behind a load balancer and distribute requests. But databases store state, and distributing state across machines introduces new challenges. Replication introduces lag, sharding introduces cross-shard queries and data rebalancing, and techniques like consistent hashing help manage that complexity, but they don't remove it. So, scaling a database means transforming a single machine into a distributed system. That's why many engineering teams try to keep their database unsharded for as long as possible. If you enjoyed this breakdown of database scaling, let me know on which topic you would like to see next. Thank you guys. Bye.